Hey team, I'm Maddie. Welcome to ScienceSideUp and happy Star Wars Day. I've got my Star Wars shirt, I have my lightsaber chopsticks, I've got bobblehead Obi-Wan, I have my Star Wars mug, and I thought that in honor of Star Wars Day, it might be fun to talk about the 4 fundamental forces. So when I say the word force, I bet your mind goes to a contact force, something like this. But that's not what I or physicists mean when we talk about fundamental forces. So there are 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. I thought we'd start by talking about what each of these forces has in common so that maybe we can get a start on understanding what a force really is at its core. And then we'll go through each of them individually. The first thing that all 4 of these forces have in common is that they can act on an object or a particle without actually touching it. Right? And when I say act on, I mean it can make it move, right? So these are all either going to have the ability to repel or attract or both that object or particle, depending on some property of that object or particle. The second thing that all 4 of these have in common is that they're going to act on a particle based off of a specific property that that particle has. So for example, the one you're probably most familiar with here is going to be gravity. Gravity acts on objects that have mass. So let's dig into gravity a little bit more because it's probably the force you're most familiar with. Okay, so this is the equation that represents gravitational force. It says that the force due to gravity that acts between 2 objects is equal to the gravitational constant times the mass of the first object, the mass of the second object, and then you divide that by the distance between the objects squared. One of the things that's interesting about gravity is that it's always an attractive force. That is, it's always going to try to pull things together. And so that's because negative mass isn't a thing, right? So our mass has to be positive, right? If we're going to be in existence. And so the gravitational constant, that's positive, and then the distance between 2 objects is always positive. And so that's gravity. So let's move on to electromagnetism. So the electromagnetic force is a unified term to talk about the force that acts between objects that have charge or a magnetic field. And we know from like Maxwell's equations that electric charge, electric fields, and magnetic fields, all of these things are really related and fundamentally kind of the same thing. And when I say fundamentally, I mean like down at the quantum physics level. But I also wrote up an equation for the electrostatic force. So the electrostatic force, it's going to be like one way the electromagnetic force can manifest. And the electrostatic force is nice because the equation looks an awful lot like the one we just looked at for gravity. So we have a constant, we have two values here. Those q's represent the charge of the particle, and then divided by the distance between the particles squared. Now, the electrostatic force, unlike gravity, can be either attractive or repulsive, because we can have something with a positive charge or a negative charge. So in this example, if we have a positive charge and a negative charge, that's going to be attractive, right? They're going to try to move towards each other. But if we flipped the sign around on this particle, now we're going to have a repulsive force. So these guys, if they're the same charge, would try to move away from each other. And if we're thinking more generally of the electromagnetic force, it's the same idea if you have, say, a bar magnet. I can easily enough connect a north pole and a south pole of a magnet. That would be attractive, right? Opposites attract. But if we flipped one of these around, they would try to push each other apart. That's the concept of the electromagnetic force. I'm gonna write down a version of Maxwell's equations really quick to show the unification. Okay, Maxwell's equations. See, even I had to look them up. The reason that I wrote these on the board is to kind of try to illustrate the complexity of the mathematics and the specifics of these forces as we're starting to move to smaller scales. So you guys have some familiarity with what gravity is and how magnets work, right? But the strong nuclear force and the weak nuclear force, that's going to we're getting into some pretty complicated quantum physics-y realms. And so I brought in Maxwell's equations, one, because they're beautiful, and two, to highlight some of the complexity that we're getting into, and maybe why from now on I'm not going to have a nice simple equation for you. But just to kind of read these in English for you guys instead of in math, what this says is that the strength of an electric field is equal to the density of the charged particles. This one actually tells us that there's no such thing as what's called a magnetic monopole. All that means is that if you take a magnet and you cut it in half, you'll just end up with a new north pole and a south pole. So you'll never have a north pole by itself or a south pole by itself. They always exist together. You always have both poles. This tells me that a changing magnetic field creates an electric field. And this one tells me that a changing electric field will produce a magnetic field. These two are really important for how electromagnetic waves and electromagnetic radiation exist and traverse through the universe. Okay, but enough about this. On to the fun stuff. Let's talk about the strong nuclear force. The strong nuclear force, it's going to be a force that acts inside atoms. The furthest distance it can act on is about the size of a proton. And so the strong force isn't really something that you or I have to worry about unless we're specifically thinking about what's going on inside of an atom. And so like we showed with gravity and electromagnetic forces, we know that forces act on things because of like specific properties, right? Gravity acts on mass. Electrostatic force works on charge. Well, the nuclear strong force, it acts on quarks. So quarks are things that are smaller than neutrons and protons, In fact, neutrons and protons are made up of quarks. Specifically up and down quarks. So quarks come in 6 flavors: up, down, strange, charm, top, and bottom. A proton is made of 2 up quarks and 1 down quark. So up, up, down. Now an up quark has a charge of 2/3. And then it also has a spin of 1/2. But we'll leave spin for now. No, let's use it. Let's use it. So it has a 1/2 spin. Now a down quark is going to have a charge of -1/3, but it'll also have a spin of 1/2. So we know that a proton has a charge total of 1 plus 1. And so that's kind of nice, because if we're thinking about 2/3 plus 2/3 minus 1/3, 2/3, 2/3, 1/3, we'll get a total of 1. Sorry to make you add fractions. Now a neutron, we know has no charge, so we can already guess what type of quarks it's made of, right? So we need to have 2 down quarks, each with their -1/3 charge, to counter out the charge of 1 up quark. So the nuclear strong force acts really between the up and the down quarks. So these quarks are sort of the opposite of the other. So quarks come in pairs, right? So up and down are a pair, charm and strange are a pair. And so, yeah, so the nuclear strong force, which we'll mark as green for right now, is acting on, say, those two and those two. And then we could bring these two guys together to make an atom. This would actually be deuterium if we brought, which is a flavor of hydrogen, if we brought our proton and our neutron together. So it would act on these guys. Now the nuclear strong force, like gravity, it's going to be attractive. It's going to always be an attractive force. So the nuclear strong force is super important for holding atoms together, because if we started making something with more protons than hydrogen, so even helium, we have the electrostatic force working against us. It would try to repel the 2 protons in the nucleus of that helium atom. But the nuclear strong force is there to bring them together. So that's the nuclear strong force. We've only got one more to go, and it's the weirdest one. So let's talk about the nuclear weak force. The nuclear weak force acts on an even smaller distance than the nuclear strong force. It acts at about a maximum length of like 1/100th the length of a proton. So why is the weak force something that we care about? Great question. It's actually what's responsible for most types of radioactive decay. It allows fusion to occur. So we really do need the nuclear weak force for kind of our universe to make sense. The nuclear weak force. There is a link in the description to a really great video put out by Fermi Labs that goes into a lot more information on the nuclear weak force if you want a more in-depth look, because we're just going to talk about this pretty basically. So the nuclear weak force is interesting because it actually cares about 2 things. It cares about the handedness, that is a real physics term, the handedness of the particle's spin, and it also cares whether the particle is matter or antimatter. So on the board, I've drawn an electron and a positron. So the electron and the positron are matter and antimatter particles of each other. So I talk a little bit about electrons and positrons specifically in my video on beta minus decay and beta radiation, which is Isaac Asimov's positronic brain. And then I also talk about matter-antimatter stuff in the video Twinsies. So if you're interested in that, those would maybe be some videos to check out afterwards. You know, I'll put a link in the description for you guys. So I have drawn this electron with the arrow here indicates its spin. So it's going to be spinning in this way. So you can think of that as it's spinning, if you were looking at the top of it, it's spinning clockwise. So that's a left-handed spin. And the positron is spinning the other way. If you're looking down on top of it, it's spinning counterclockwise. And that's called a right-handed spin. So the weak nuclear force can act on matter that has left-handed spin or antimatter with right-handed spin, but not any other combination of those two properties. So for example, the weak force is very important for beta minus decay. So let's think about a free neutron flying through space all on its lonesome. Now, this neutron will actually decay by beta minus decay into a proton, an electron, and an antineutrino. One thing that's very cool about the nuclear weak force is that it's the only force that's able to change the flavor of the quark, right? So we had to take one of the down quarks in our neutron and turn it into an up quark for the proton, right? So anyway, and then there's consequences to that because we have to conserve spin and charge and momentum and things like that. And then notice that here we have matter. So electron is matter, but an antineutrino is antimatter. So these guys, we know we're actually going to have opposite spin. So that should have that spin, that should have that spin. Did I do that right? No. Sorry. There we go. That's the right arrows for the spin. And so these guys are going to kind of fly off in opposite directions. But they are being acted upon by that weak force. I know it's complicated. Nuclear weak force is weird and complicated, but also very cool. The coolest things in physics are weird and very complicated. Okay, team, well, that's all I've got for you today. I hope you enjoy your Star Wars day. May the 4th be with you. And I will see you all next time. Please help me reach my goal of 1,000 subscribers by the end of the year. Our first goal is to hit 300. So if you haven't subscribed, please hit that red button. Give this video a like, and I will see you all next time. Okay, bye team. Hey team, so if you liked the music that I was using throughout this video, that was all done by Closed for Sunday. So there are links in the descriptions to where you can find more of their really amazing music on YouTube, Spotify, and Soundcloud down in the description. So yeah, go check them out, and you guys are awesome.